Okay, so now we're going to talk about like real chemistry, atoms and elements, the structure of them, and then hopefully on Monday we will be able to cover at least a chunk of bonding. Okay. Considering time constraints, I think we're gonna limit ourselves to Unit 4 today. Anyway, so oh, I didn't edit this, guys. Okay, sorry about that. This is kind of, I'm gonna skip the really unimportant bits. Okay, and we'll focus on the consequential slides instead. So first, we're gonna chat about the concept of an element. Okay, so what are the elements? First of all, they are pure substances. They make up everything. Okay, and the main feature of an element is that it cannot be broken down into simpler substances, or should I say other substances. I'm going to add a little comment. By chemical methods. I don't know if you've heard much about alchemy, but that was pretty the whole idea of alchemists, to find a way to chemically convert whatever into gold. This is why I mean chemical methods. You can do chemically anything to sulfur, you're not going to convert it into phosphorus. You can use physical methods like nuclear reactions. That's a different story. Yes, that's different, okay? All elements that are known are in the periodic table on the board right there. Okay. So elements, all elements have chemical symbols. Some of them make sense, some of them don't. Okay. So these are the ones that make sense. Symbols can be 1 or 2 letters, never 3. Okay. If it's a 1-letter symbol, it is capitalized. If it's a 2-letter symbol, the first letter is capitalized, the second is not. Okay? Make sense? Okay, perfect. These tables, be able to read them. Those are common elements. Nobody's going to ask you what the chemical symbol for samarium is, but you should be able to identify all. So most of them make sense. Okay, good. Most of them make sense. I'm going to highlight the ones that kind of don't. So okay, copper, Cu, not Co. Or Cp, because cuprum is Latin. Gold, aurum, okay, same, ferrum, iron, Fe, this is why iron is Fe, lead, Pb. So mercury is Hg, because it's called hydrargyrum, and if we want to dive deeper into language intricacies of this, it literally means liquid silver. Okay? So potassium is kind of funny because in most European languages, it is calcium or some variant of it. Okay? At least in Romanian languages. Silver, argentum. Okay? I don't know if you studied French, argent is money. Pretty much silver. Natrium, this is why sodium is Na, because it's natrium in many other languages. And tin is stanum. This is why I said. Okay? We don't talk about, what is that, SB? I forgot what's the term in English, but like SB, element number 51, it's another example. I don't think in English it's stebium. I don't remember what the element, this element is called in English. I studied chemistry in Russian. Okay. Mercury is toxic. Okay. It is true. But what's most toxic about mercury is vapors. It was used at some point to treat constipation. I think it's quite hilarious the way it did treat the constipation. You drink mercury, it's heavy. It's like ramming through your intestines, just pushing stuff out, okay? And yeah, you would poop out mercury in unchanged format pretty much because it's not particularly reactive. Vapors is the different story. The most toxic thing is mercury in organic compounds or food. If I will drink the mercury, no, I wouldn't die. I'd be fine. I mean, if I would do it like every day, I would probably eventually get mercury poisoning. But a good example, so it is recommended not to eat too much of certain ocean fish, tuna, swordfish, examples. And there are organic compounds that contain mercury. Our professor of chem when I was in college, he told us he worked on them in 2 years. He had heart problems, his skin was terrible, his hair fell out, like he was basically slowly poisoned. Okay. Contact with skin, not as much. Skin is pretty impenetrable and mercury is not terribly reactive. But yeah, the biggest problem with the mercury is that it is cumulative. It gets out of the body very, very slowly. Okay. Yeah, there are a lot of side effects of the mercury exposure. So now there will be some corrections here. So we're going to talk about periodic table. But if you will be reviewing the slide, you see this statement? It is wrong. So periodic table puts elements in the order of increasing atomic number. We're going to get back to this when we talk about the structure of an atom. Sounds good? Okay. So we're going to figure out how you work with the periodic tables. Yes, in 1869, supposedly, Dmitry Mendeleev saw periodic table in his sleep. Okay, but it was a brainchild of many people before him. Like he was standing on the shoulders of giants. He was mostly famous in Russia for actually making suitcases. I mean, he was a brilliant scientist, but people knew him as suitcase master. It was his hobby. So, no. By increasing atomic number. Well, to be fair to Mendeleev, when he was arranging elements, he used increasing atomic mass. Okay, but eventually it boiled down to the fact that we need to give all these elements a specific number, which is like right? Like 1, 2, 3, and so on. But these numbers aren't merely just order in which they go. They actually are rooted in a fundamental property of an element. Okay? So structurally, you have periods which are horizontal and columns, also known as groups, which are vertical. that make sense, everybody? So, if you would turn, well, if we go back here, or you can look at the periodic table behind you, you can see that the periods are numbered from 1 to 7. Okay? And you can see that the columns have two sort of ways to get numbered. The old way, when you have 1A, 2A, then all those B's, okay? Does that make sense? And just simple numbering from 1 to 18. When I was studying chemistry, when I was learning it, the main way was 1A, 2A, 3A, 4A, or 3B, 4B, because A groups were considered to be major groups, and B groups were transitional metals, okay? Now I think 1 through 18 makes much more sense. Just easier, okay? So A, which we called major group, are representative elements that have a pretty well-defined properties, whether they are metals or non-metals. And letter B, the transition elements, if you look at the table behind you so I don't have to scroll back and forth, you see it's a new numbering. It's numbering from 1 to 18 for the groups. Can you see that? And the groups 3 to 12, they include transition elements or transition metals. Okay, this is why on that old version they all have B in them. Okay, and you can see there's like a lot of confusion that can be created because of this, like this. These three elements all in the group 8B, you know, it's kind of makes no sense. Anyway, so I'm going to be using, just to make it clear, I'm going to be using the modern numeration for groups 1 through 18. Okay, sounds good? Now, there are certain things that you will have to memorize regarding the periodic table. So upper right corner are nonmetals. Okay? And you can see this zigzag. Okay? Everything to the right of that zigzag are nonmetals with some minor exceptions. Okay? So boron, silicon, arsenic, tellurium, and astatine, as well as germanium, stibbium, and polonium, those are considered to be metalloids. And I don't remember what it's named for. It's one of the recent elements. Those are considered to be metalloids, right? So memorize it. In all fairness, if we start looking at actual properties, like polonium is pretty much a metal, boron and silicon and arsenic are pretty much non-metals based on the properties. Okay? Everything to the left of that zigzag line is going to be metals. Good? Okay, cool. So what is the difference between metals and non-metals? This, first of all. Most metals are shiny solids. Again, if you look back at this table that is behind you, it's actually quite useful. Do you see that the colors of the elements are different? If it's black, it is solid at, normal conditions like room temperature. Make sense? If it is not filled, those elements do not exist in nature. They can only be obtained artificially, but that's beyond the point. If it's blue, those are liquids at the room temperature. So we have two liquids bromine, number 35, and mercury, number 80. And if it's red, it's the gas at the room temperature. Okay, sounds good? Now, one tiny little comment. If you look at number 31, which is gallium, it is a solid at the room temperature. If you take it in your hand and hold it, it's going to melt. Its melting point is, I think, 34, 35 Celsius. Okay? So just, they are ductile and malleable. Okay? Different metals to different extent, they all conduct electricity. And usually the melting points, I just gave you gallium as an example, melting points are higher than the ones for nonmetal. But I can tell the melting point for mercury, negative 39 degrees Celsius. So if you would take mercury out in that cold, it would still remain liquid. Those are exceptions, obviously. Okay, good. Nonmetals. All gases that we have in the periodic table are nonmetals. Okay. Poor conductors of heat and electricity, and if you look at them, like the only solids that I can think of are selenium, carbon, iodine, selenium, sulfur, phosphorus, carbon are the solid nonmetals. So you can see that, as a matter of fact, you have more gaseous nonmetals than solids. Okay. So, metal, nonmetal, or metalloid. Go. Sodium. Bromine. You can look back at the periodic table, dude. It's there for a reason. Bromine, number 35. Metal or non-metal? Non-metal. Remember the zigzag, right? You see how boron is highlighted? You see that red line on that specific periodic table? If you start just doing zigzag, like boron just down like this, that's going to be the zigzag that separates non-metals from metals. Boron, actually, metalloid, we're going to call it MD. Manganese, number 25.
Transition metal.
Metal. Carbon. Non-metal. Make sense so far? Cool. I mean, it's kind of cool with all those macro and micro elements. So this is yes. So oxygen, carbon, hydrogen, nitrogen. You do need, so I would, as a biologist, by my second training, I would put sulfur out of macros because sulfur is in proteins. You're not going to get away from that, so it's pretty major one. Macro minerals, yes, indeed. These and these. If you don't have them, you're going to die. Okay. Again, I told you I would put sulfur into the bigger one. And then there's a bunch of trace elements. Obviously, there's a link here, just, some of the, you probably know some conditions associated with the deficiency. Iron deficiency, you would have anemia. Copper deficiency, there will be some problems with the respiratory chain. Iodine, you're going to have goiter, the thyroid problem. Other than that, you receive all those microelements from the diet. Like if you eat normal diet, you're going to receive everything. Iodine, you have to get iodized salt. But other than that, you're going to receive all the elements from the diet. Again, I'm talking about balance. If you eat kale and nothing but kale, you're not going to survive for very long. Okay? That makes sense? Don't memorize that. Please just. Now, this is going to be quite important. We're going to spend some time here. And I want you to, because this is the fundamental thing, I want you to stop me if something isn't clear, right? So we're going to chat about atoms. This is actually a famous photograph for which people from IBM received Nobel Prize. Well, not photograph, but they developed the technique to photograph individual atoms. So each of these is the atom of gold. So, gold. This is gold, yes. This. Because, there's a reason behind it. Gold is extremely malleable, and you can basically make a layer that is one gold atom thick. This is how they managed to do that. Okay, so every element consists of atoms, of the same kind. So if you take a sample of, well, you worked with this zinc, that little brick that you had on Monday, all atoms in that piece of zinc would be the same. Okay? Sounds good? Now, the reason why it's called a atom is from Greek atomos, indivisible. There is no chemical way to break atom apart, and atom has all the same chemical characteristics, and it gives chemical characteristics to an element. Does that make sense? So the first, well, technically the first idea of atoms was like by Democritus, down like in ancient Greek or whatever, but the actual appropriate atomic theory was formulated by John Dalton. Yes, Daltonism or color blindness was named after him. So Dalton suggested several things regarding atoms, okay, but he was applying it more to the compounds here. So here are Dalton's ideas. He didn't know what the atom was. He didn't know the structure, but he said, okay, every piece of matter consists of atoms, period. That's it. Second, in a given element, atoms are identical to one another. Okay? Atoms of one element are different from atoms of another element. Fair? So far? Cool. If you combine atoms of two elements, it's going to form a compound. Okay? Every compound has the same kinds of atoms and same number of each kind of atom, no matter where you get this compound from. See the example of water. Okay? Sounds good? And the definition of a chemical reaction is the rearrangement, separation, or combination of atoms. So this, never created or destroyed. Okay? Sounds good? Good? So, I'm trying to think of a reasonable example to show the combination, rearrangement, separation, or combination. So let's say you have carbon, an element, everybody agrees with me, and oxygen, also an element. Oxygen exists as a molecule that consists of two atoms. That number 2 means that in a molecule of oxygen there are two oxygen atoms that are identical. Are you with me? So burn carbon in oxygen, you get carbon dioxide. How many carbon atoms do you have on the left? On the right? Nope. 1. Right? Just 1 carbon. How many oxygen atoms do you have on the left? 2. On the right? Also 2. Okay, that subscript shows you how many atoms of an element that is before that. So, Thomson, a British scientist, and then Rutherford, they did some experiments with a lot of stuff, actually not only electricity, but eventually they discovered, not only there were other people who discovered electrons, for instance, that atoms consist of 3 what's called subatomic particles: protons, neutrons, and electrons. Okay? And it has also been demonstrated that protons are positive and electrons are negative. Neutrons have no charge. Good? So here's the conundrum. Turns out that positive and negative charges in the atom are separated in space. As we're going to see, positive charges are in the nucleus, negative charges are outside. But if you put 2 positive charges next to each other, they're going to repel. Right? Make sense? 2 negative charges are also going to repel, and we have to keep it in mind, because when we're going to talk about chemical bonds and structure of the molecules, we need to remember that charges with the same sign repel each other. Well, unlike charges attract. Right? So far, so good? So this is the atomic structure. If you would look at the atom, see, this is the nucleus. It's super tiny. Within the nucleus, we have neutron. What is the charge on the neutron? Nothing. And I have positively charged proton. Does that make sense? Electrons are kind of flying on the outskirts, orbiting the nucleus. So far, so good? So now we're going to talk about the mass and the atomic number eventually. So what is the atomic mass unit? Atomic mass unit, which it is a mass equivalent to 1/12 of the mass of the carbon. If you would look at the periodic table and look at the carbon number 6, you see the red number under the letter C. Throw away all the numbers after the decimal point, and you're going to get 12, right? So you divide it by 12. 12 divided by 12 is 1, so this is 1 atomic unit. So here's the deal. You see this? That the proton has a mass slightly more than 1 atomic unit. Do we care about that number 7 at the end? What do you think? We don't. For our intents and purposes, the mass of a proton is 1. A mass of a neutron is also 1. All good? Question so far? Cool. Say again? Well, because we only can be imprecise if we're precise in the first place. So we acknowledge that the mass of a neutron or mass of a proton, if measured exactly, is going to be a tiny bit more. But for our calculations, we're going to ignore it because it's not going to affect our calculations in any reasonable, noticeable way. Does that make sense? Awesome. An electron. So I'm trying to think of a comparison. Like, my body mass about 80 kilograms. So 1,000th of it would be like less than a gram, and then cut it in half. So like it's probably a mass of, I don't know, all the hair in my head, which says a lot, it's not great. So what I'm saying is we can basically assign the mass of an electron as 0. Okay? So 1, 1, 0. For our calculations, we're not going to take the mass of an electron into account. Making sense? Good? So just, again, when we talk about mass, these numbers are what matters. Okay? And the symbols you can see, if we talk about protons, they sometimes have a plus. Neutrons sometimes have 0, meaning that they're not charged, and electrons have minus to show that it's negative. So now we're going to talk about fundamental concepts. What is an atomic number and what is an atomic mass? This number of protons is equivalent to an atomic number. Okay? So this is why I was so fussy about the statement that in periodic table elements are arranged in order of increasing atomic masses. So take a glance. It's actually quite fun. So if you look at, I'm gonna ask you to start tracing elements from 15 to 20. Okay. So 15 is phosphorus. What is the number? 15. No, 15. The number is 15. Okay, I didn't say it. My fault. So the atomic number is the blue number in the upper right corner. Okay? 15 is atomic number. First of all, what does that mean in terms of the number of protons in an atom of phosphorus? It's 15, right? It's 15 protons, right? Sulfur? Sulfur. How many protons? Yes. Chlorine? Argon? 80. Yeah, potassium 19 and calcium 20. Okay, does that make sense? Which means if you take any atom of calcium, it's going to have 20 protons. Okay, now hear me out. If you become some tiny little atomic Oompa Loompa and take this one proton out and go from 20 protons to 19 protons, is that still calcium? No, what is it? It's potassium, right? That makes sense? Now, I want you to look at the red numbers at the bottom. And I'm going to shorten it. So feel free to round it up. For argon, that bottom number, when you round it up to like the whole number, what is it? 40. For potassium? 39. And then for calcium, 40 again. Do you see that? So this is why I say, and if you kind of do the same with cobalt and nickel, they have the same atomic number. They have the same mass number at the bottom. So my point is, it is not scientifically accurate to say that the elements are arranged in order of increasing mass. See what I'm saying? Yeah, numbers are fine, but look at the bottom numbers, the mass numbers. It's 59 and 59, right? So it's not increasing, really. See that? So this is why I have a bit of a fuss. And then you can look 52, 53 actually. So tellurium is 128 and iodine is 127, I think. My vision is not great. Okay, that makes sense? So the atomic number, which characterizes the number of protons, is always on top. So this is what we talked about. Protons, they determine the identity of an element. You see what I'm trying to say? Like if you have an atom which has 12 protons. You can look right there. 12 protons, it's magnesium. That's it. That's all you need to know. Okay? So we got this. We said, so you must remember that atomic number is equivalent to the number of protons. Okay? So, tell me, fluorine, how many protons? Fluorine is F. Potassium, which is K. And barium, which is Ba. Sixth period. 56. 56. Okay? Atoms are electrically neutral, which means that they have to have a net charge of 0. What is the charge of a proton? +1. So you have to equilibrate each proton, right? By a negative charge. Which particle has a negative charge? An electron. So, calcium. Atomic number is 20. 20 protons, 20 electrons. Okay? You may ask yourself a question. Why don't we say that atomic number is equivalent to the number of electrons as well? We can say this if we will specify that the atomic number is equivalent to the number of electrons in an electrically neutral atom. You can add or remove electrons to and from the atom, creating ions. We're going to chat about it as well. But so far, does that make sense? It should be a mantra. Atomic number is the number of protons. Mass number. For our intents and purposes, what is the mass in atomic mass units of one proton? 1. 1 neutron? No. Neutron is also 1. What is 0? Electrons. So we're essentially saying that the mass of an atom is number of protons plus the number of neutrons. This is the definition of an atomic mass or a mass number. All good? Fantastic. So, in order to know how many neutrons an atom has, okay, we can take a mass number and subtract the atomic number. Does that make sense to you or not? A good illustration to this would be to remember what is the definition of it. Check this out. Can I say that the mass number is protons plus neutrons? Can I say that atomic number is the number of protons? There you go. Okay? Looks good? Oh, this is one of my favorites. Before we get to isotopes, let me ask you a question. I will take an atom of phosphorus, B. How many protons its nucleus is going to have? B. 15 group, third period. No. Just, I'm going to take one atom of phosphorus. One atom. How many protons am I going to find in this one atom? It's not 15. 15. 15. Look, third period, third P. Okay, third period, right? 15th group. Can you see that? The crossroads of 2?
I don't know what you're saying.
Okay, so remember the groups are vertical, periods are horizontal. Right? No. Group is vertical, period is horizontal. So can you see the third? It's not continuous. You see what I'm saying? It's not continuous. Line 3 in the table. Can you see that?
Yeah.
Sodium, magnesium, aluminum, silicon, then phosphorus. Okay? Did you trace it down to phosphorus? Line 3 is not continuous. Yes, there's a gap. There's a gap. Okay? So phosphorus has an atomic number of 15, which means, right, it has 15 protons. Everybody agrees? Does it say anything about neutrons? Really? Why do you think so? Well, first of all, if you round it up, it's 31. Right? So 16. Okay, fine. But here's the deal. I'm going to write something down for you. So phosphorus, okay, with the mass number, that's what Aubrey said, 31, right? Mass number. You with me? If you're not following me, just stop me right there. Look at phosphorus there. You see the red number at the bottom of the cell? Round it up to the whole number. What is it going to be? 31. This, let's say the mass number for a particular phosphorus atom is 31. The atomic number is 15. Okay? Which transpires into 15 protons. Everybody agrees? How many neutrons left then? 16 neutrons. All good? Yours truly, at the beginning of his research career, worked with radioactive phosphorus, which has a mass number of 32. Okay? How many protons did this radioactive phosphorus have? 15, which means 15 protons, but how many neutrons now? Does everybody follow? So, isotopes. Same element, okay, but different number of neutrons. So essentially, atoms of the same, when we say all atoms of the same element are identical, we're actually not entirely correct. They can be different isotopes. You see what I'm trying to say? So, the definition of an isotope: same number of protons, different number of neutrons. Am I making sense? Now, if you look at this, magnesium example, if you will sample a magnesium string, it's going to have some magnesium with an atomic mass number 24. See that? Some atoms which have 13 neutrons instead of 12, and some that have 14. Okay? That makes sense. So, this is a great example. If you look at the periodic table here, or you look at the number here, you see this 24.31, okay? This is the mass number that takes into account the fact that magnesium has 3 different isotopes, and that these isotopes have different frequency of occurring. Am I making sense? So most common is the isotope, a type of atoms with 12 protons and 12 neutrons. Everybody follows me on that? Right? All good? So 12 protons, that's this, and 12 neutrons. Now this guy, how many protons does it have? 12. How many neutrons? 13 Does that make sense? Huh? So it's fine. It's the learning experience. What about that right one? How many protons? How many neutrons? Okay? Does that make sense? Thank you. So, let's chat about specific... For God's sakes. Dude. Okay, better. I'm going to just make it large, okay? So here's the magnesium, right? 26 is what? It's the mass number, right? Okay. Kaylee, do follow. 12 is the atomic number. What is the mass number? By definition. No. What does it consist of? Protons and atomic number. Protons only, right? So the difference between the two is what? I want a response. 14, right? But the difference between the two is essentially the number of neutrons. Good? Okay. So, before we're actually going to start talking about Unit 6, so we for sure can finish it on Monday and you have that week to study. But here's another, what couple of things, fundamental things to understand about isotopes. First of all, I'm going to ask you questions. You're going to answer. No, one question. Isotopes, do they have same chemical properties? Yes. Magnesium 26, magnesium 25, magnesium 24 can be engaged in exactly the same types of chemical reactions. And they're going to behave exactly the same in those chemical reactions. Because if neutrons are different, it doesn't matter. It's protons that determine the chemical character. Okay? Second, how do you know which isotope is most common? Look at uranium-92, number 92, bottom line. Okay? Number 92, yeah, fourth from the left. See that? U? Yep, okay, uranium. So, the number at the bottom, rounded up. This is the most common isotope, 238. It's also non-radioactive. The biggest technology, you've heard about Manhattan Project? Manhattan Project, the nuclear bomb. 1945, Americans created nuclear bomb. The biggest advance of that technology was not how to make a nuclear bomb itself. Everybody knew. It was how to separate the isotope 235, which is radioactive and can be used for nuclear bomb, from 238. That's it. You can't separate them chemically. This is kind of a secret that Soviets stole from the US in 1946 and made their own atomic bomb. I'm pretty fascinated with that whole thing. Okay, does that make sense? Okay, again, understand the concept of isotopes, understand the concept of protons, neutrons in the nucleus. And remember, electrons do not contribute.